Okay, we're recording and in business. Okay, so here's where we were last time. We were talking about doing integrals in spherical coordinates. We were mostly done with that, but not quite. A couple more examples I want to show y'all. Here we have another ball offset. Right? So this time, instead of having it center up here on the z-axis like we talked about previously, this time the center is over here on the y-axis. So a little bit different. And it does change how the integral gets the details of how it works out somewhat. So here's the big idea. As usual, very first thing we do is we write this down. Right? First thing we write down is not just d rho d phi d theta. We don't ever write down d rho d phi d theta by itself. Right? That's just asking for trouble. Always write down the full dx, dy, dz, right? Which is what it really is. So stretching factor and spherical differential. So rho squared sine phi d rho d phi d theta all at once. Make sure you don't forget that stretching factor. That said, then theta bounds. Imagine what these slices look like. They don't hit all the way around. There's kind of a first slice that's over here in the direction of the x-axis. So theta equals 0 to start. And then it goes around for a ways, but then there's a last slice. This last slice is over here in the direction of the negative x-axis, where theta is pi. Does everybody see that? Now again, this is just geometric appeal. You got to have a good picture. You got to think about, where. Let's see. In this case, where does the sphere intersect? And in fact, it intersects the z-axis just at the origin. Right? It does not surround the z-axis. It just intersects at that single point, and so you just get this kind of this half range of values for theta. Okay. All right. I remind you. Again, really important to have a good picture. It doesn't have to be publishable beautiful, but it needs to be representative, qualitatively accurate, that kind of thing. Okay. All right. So now we look at a given theta slice, and again, geometric appeal, but a theta slice. I like to draw looking straight at it. It's easier to see. And geometric appeal in this case, that cross section is, it's a disc. I mean, I think that's a pretty easy pitch. If you have a ball and you take a slice, you get a disc. Right? So that being a disc and the sphere having been tangent to the z-axis at the origin, the phi slices, which, kind of like this, right? The first one is going to be straight up, where phi equals 0. The last one is going to be, straight down. Phi equals pi. Everybody see that from the picture? Okay. All right. And then lastly, now we look at a phi slice of, let me do this in a different color. At a phi slice of a theta slice. And on that phi slice of that theta slice, our range of values of rho is like that. Rho starts there clearly at 0. Where it ends is the more interesting point. Where it ends there on the boundary of that disk, if you will, on the circle, which if you think about it, where that really is over here on our original three-dimensional picture, which means it's on our sphere. So you have a spherical coordinates conversion problem. Being as it's on the sphere, I need to know how to write that equation. Again, make sure you can do that. This is what it turns out to be, but make sure that you can take the given description of this sphere, write down the rectangular equation from, high school algebra knowledge, and then convert by plugging in the conversion formulas. Okay. And that formula for rho is your upper bound then for rho. Okay. All right. The last one I'm going to show you is really kind of more for the art, the drawing trick involved. And what we have here is, roughly speaking, we're looking at this shape here. It's what's inside of this upper ball, but then outside, right, outside of this lower ball. So imagine this, take the top ball, and then the lower ball is kind of cutting a hole out of the bottom of it, if you will. Okay, so what I've got in purple there is the picture. Well, it's kind of a picture, and let me point out part of what makes this a good example is that it's so hard to draw the picture. After all, there is kind of a little. I mean, it looks like we've got a couple of vertices here, but we don't, right? I mean, in fact, there's kind of a lip that kind of goes around like this. And so it's hard to draw that the thing has kind of a circular lip bottom there, but it also has a sort of a little indentation, if you will, in the bottom. So how do you draw that without making it look solid or making it look like there's just no lip at all? It's a tough draw, honestly. So when you have something that's hard to draw, one could argue it's even harder to think through, well, then what do the cross sections of it look like? Right? So the trick I want to point out here is you don't actually have to, in this case, actually visualize what the solid itself looks like. Instead, think about, as you're taking your theta slices, right, and after you've made the easy observation that, well, theta goes all the way around. I mean, there is all this solid up here. It clearly sort of surrounds the z-axis. So, I mean, this part is clear. But thinking about what these theta cross sections look like, don't think about the solid itself. Think about the balls that make up the solid. And what are their cross sections? And those are easier questions. So in particular, this ball right there, what's a cross section of that ball by one of these theta planes? Well, that's no problem. It's a little half disc, right? No sweat. Here it is. Right, taking that. Let's see, what color did I use? Blue, I believe. Yeah, taking a theta slice of a ball gives you a half disc. And then now likewise, looking at the lower ball, this is what we're sort of cutting out of the upper ball. That, well, still, it's just a ball. And taking a half plane slice of a ball, no problem. It's another half disc. And it's very easy then, looking at this picture, to ask, okay, what is it that was, inside of the purple but outside of the red? And, well, then it's, like I say, easy to see that what we've actually got then is something like this. Okay, so for whatever it's worth, I think it's a nice trick. Slice up the pieces that go into defining your solid just as good as slicing up your solid. Okay, and artistically easier. So again, you got to think through the ranges of values. I'm going to point out here we have we can define that value of phi. Again, you could play trig games and write down the equations of these both of these circles and solve for phi. But it's much easier to observe that this and this are radii of that circle, and this is a radius of that circle, and all of those radii are known to be 1, so we have an equilateral triangle, and it's the same trick that we pulled back in polar coordinates, just kind of a different context. So always be on the lookout again for that kind of convenience that saves you loads of trouble in finding that phi bound. Everybody all right? Yes?
Why would it be 0?
Yeah. So the lower bound, yeah. So if you look at what phi slices do, here's an arbitrary phi slice. It's actually this thing right there, right? The lower bound for phi is going to be there. That's where phi starts.
Okay, I thought you started from the horizontal.
No. So you always start. Phi is always defined as an angle measured from the vertical part of the upward part of the z-axis. That's right. Yeah. Okay, so that's the end of part 2 of section 5.5. I'm sure you noticed on the content syllabus I broke it into 3 parts because otherwise we'd have an entire week with no homework assigned because we weren't done with the section yet. So anyway, on to part 3. I'm going to move really quickly in this part because In fact, none of this is really in the book. The author kind of assumes it in several places, like it's trivial and obvious and, barely worthy of mention, and I don't think that's fair. I think there's some significant ideas here. I also think these are really powerful ideas. Symmetry theorems for evaluating integrals can take an otherwise complicated-looking, super inconvenient integral and turn it into a snap. A couple of quick, clever observations, and integral 0. Just boom. Very powerful. So let me show you the theorem before I say more tangential notes. So you've already seen a symmetry theorem back in single variable calculus. It was probably written differently, but there was this notion of an odd function discussed. I hope everybody's seen this before. This is an odd function. They call it odd because odd powers of x have this feature, that a minus sign before you apply the function turns into a minus sign after you apply the function. Right? Neat trick. It's nice when a function has that feature. And you've probably, anyway, I'm going to, 50-50, you've seen this idea before. I'm going to talk about a symmetric interval. And you've probably seen this as an interval from like negative k to k, or, negative a to a, something like that, where the lower bound and the upper bound are negatives of each other. And I'm going to say symmetric because you can say it's symmetric over the origin. If you were to flip it around the origin or reflect through the origin, however you want to say it, you get the same thing back. And I'm going to describe that, though, not by what the bounds are, but I want to describe it in a more general way, as this is an interval where anytime you have a point in the interval, the negative of the point is also in the interval. And I don't think it's too hard to persuade yourself that, an interval from negative a to a will always have this feature. And vice versa. Okay. So the theorem, again, that I think everybody's seen before is if you have an odd function over a symmetric domain, the integral is 0. And it would have been written differently. It would have been written as integral from negative a to a of f of x dx. Equals 0. And again, reminder, this means exactly the same thing as this. I'm using this notation because you've probably seen this coming already. Whenever I do single variable calculus in this class, it's because I'm laying groundwork to segue into a multivariable version of it. And so in multivariable, we don't really have that notation exactly. We have this kind of subscripty sort of notation. So, okay. All right. Now, why is this true? And a couple different ways you can see it. The Riemann sum point of view, I think, is very satisfying. If you've got an interval from negative a to a, then when you break up that interval into pieces, like you've got this little piece over here, and then you've got this little piece over here, they always pair up by reflections. You can say, well, whichever piece I'm looking at, I can look at its reflection piece. And if this piece is part of my interval, well, then its reflection also part of my interval because my interval is symmetric. And I further know that the value of the function over here and the value of the function over here, those are negatives of each other because of the oddness. The known oddness of the function. And so if you look at the two terms, you look at the term of the Riemann sum term corresponding to this piece, the Riemann sum term corresponding to that piece, well, they're negatives, and so they cancel in the summation. And so the whole thing, every term cancels with its reflection over on the other side. And so there's nothing left. So again, I think that's a pretty easy pitch. I'm going to point out now a different way that you can think about it, and this is a little bit less hand-wavy, I suppose, a little bit more sort of like right down to business. You can prove it with a substitution, aka a change of variables, and you may or may not have seen this argument in a single variable calculus class. Not that you couldn't, but I just think typically they probably don't. So here's this is a lovely little argument. You got an integral, odd function, symmetric domain. Well, the fact that it has a symmetric domain means that it is its own reflection, right? So in other words, when you put in a minus sign, which is what this g function does, you're effectively reflecting over the origin and nothing happens. Same interval. Then I'm going to do a pullback, aka a substitution. And remember, with the substitution, all you do is you plug in the substitution. Don't forget your stretching factor. Right? This is a reflection. Reflections, of course, don't change sizes. And so the stretching factor is 1. So we invoke the symmetry. We do a change of variables, aka a pullback. Don't forget, the reflection is a minus sign. And then we use the oddness. The oddness pulls out that minus sign, and the result is that the integral I'm interested in is its own negative. And if an integral is, if anything, is its own negative, then it's 0. Right, so that's the argument. And you can explicitly see where we use the symmetry. Why is it important that the domain be symmetric? We need that symmetry to be able to pull off this first step. Why does it matter that the function be odd? Well, we need the oddness so that this minus sign will come out, and so that I can, finish the argument. Okay. All right. That's all single variable. And with that groundwork laid, we're now going to talk about a two-dimensional version. And everything that I've said about single variable symmetry, there is a two-dimensional version of it. Let's talk about reflections first. So with single variable, we talked about, here we go. So we talked about given some value, you can look at the negative of the value, and I noted that you can think of that as reflection over the origin. Right? It's just, the mirror image on the other side of the origin. Well, you can do that with any line in the plane. With any line, you can talk about, for a given point x, where is its reflection? So, you could reflect over the x-axis. You could reflect over the y-axis. I'm just going to point out, you can also reflect over any line you want. And it's just exactly this picture. It's exactly what you would think it would be. It's, if you're looking in the mirror, where is the person that you're looking at? That's what it's called, the reflection. Okay. Odd symmetry, totally analogous. It's that if you put, now this is where we would have put a minus sign on the input to the function, but keep in mind now we're generalizing, thinking of that minus sign as a reflection, generalizing this as any reflection, and that when you put a reflection in, you get a minus sign out. That's what we mean by odd symmetry. Totally analogous to the single variable equivalent. What does it mean for a domain to be symmetric? Well, again, exactly the analogous thing. Anytime you have a point in the set, its reflection must also be in the set. Right? So, totally analogous ideas. And with those established, here's our big theorem. And this is so big, it's so powerful. You can compute so much stuff with so little effort with this theorem. It's totally awesome. If you have an odd function integrated over a symmetric domain, your integral is 0. Fantastic little result. Now I emphasize, before we get to seeing why this is true, it's very important, both of the conditions must hold. This is not a one or the other kind of a deal. It's very dangerous, because a lot of students will get, justifiably excited about this theorem. It's so powerful, it's going to save me so much work. Oh my gosh, it's fantastic. And they'll see a symmetric domain, forget to check if the function's odd. And if it's not, then it doesn't work. And vice versa. You might see that you have an odd function, but forget to check whether the domain is symmetric. And again, likewise, you need both for the argument to work. The other thing that a lot of students forget, the others you might say landmine here, is the line. It's got to be the same line for each of the properties. So it is absolutely insufficient to have a function that's odd over one line and a domain that's symmetric over a different line. No good. Right? They have to be the same line. Okay, so very careful about those, please. Let's see why this is true with those warnings made. Here's the equivalent substitution argument. Keep in mind now, when we're in two dimensions, what we used to call substitutions, we now call change of variables. Okay? Well, there's symmetry of the domain. If you have a symmetric domain, it is its own reflection. Here we do a pullback, right? Plug in the reflection. Don't forget your stretching factor. Again, it's a reflection. When you do a reflection, nothing changes size, so the stretching factor is 1. Here's the oddness. This reflection causes a minus sign on the outside. This is what it means for f to be an odd function. And here we are again. This integral is its own negative, and therefore it's 0. So, pretty straightforward argument. Same argument that we did with the single variable version. You'll even notice I laid it out on the page deliberately in almost exactly the same layout. Okay. And again, there's a kind of if you want to see this a little bit more geometrically, a little bit less algebraically, here's a kind of a Riemann sum point of view. Here is a domain, a arbitrary random kind of domain, but which is symmetric over a line. And assuming that our function has odd symmetry, we get basically the same argument. Any little piece in your Riemann sum, because of the symmetry of the domain, there is a corresponding reflection piece on the other side. So they pair up. Because of the oddness, you get a minus sign. These pieces have the same size, but opposite values of the function. So these two terms in the Riemann sums are opposites, and they cancel, and everything cancels, and there's nothing left. So it's morally equivalent again. Anyway, there you go. Okay, so let's see an example. Oh, sorry, question.
Just to make sure, the stretching factor is 1 because they have the same, like the domain is the same as the. What is it?
So the stretching factor is 1 because the change of variables function that we're using here is the reflection itself. Okay. And it's just that when you reflect something, whatever it is that you reflect, it flips it over, but it's the same amount of area. Okay. That's all. Yeah. Is that satisfying?
Yeah.
Okay. Anybody else? Okay. All right, let's see an example. So this looks like a really hard problem. And it would be if we went at this brute force, right? If we, headed straight at it and iterated integral and just started pounding with single variable calculus. This would be quite hard because look at all this ugly. That's the part I'm most afraid of course. Okay. All right. So the first thing I'm going to observe is my domain has a symmetry. So here's a picture of my domain. That curve, I hope I can draw this reasonably believably, something like that. And then this curve is easier to draw, something like that. And I'm just going to make a geometric appeal in symmetric. And you just kind of see it from the picture. If you don't like that, I'll point out that you can literally write down the formula for the reflection. So reflecting over this line, right, is this formula. Anytime you have a point x comma y, right, then I can talk about the reflection over here. That reflection is going to have obviously the same y-coordinate, right, because I'm reflecting over the vertical axis. So there's no up and down to the reflection. Same y-coordinate. The x-coordinate is clearly then the negative of the initial point, and so therefore, boom, there's our formula for our reflection. And if you take that formula and plug it into these equations here, you take this equation and plug it into there, and you can see that nothing happens. Right? You plug in, instead of x, you plug in minus x. Those minuses just get squared away, and same equation. So flipping over that curve doesn't change it. Thus symmetry. What do you think? All right. Now y'all know I am a big believer in explaining your reasoning, showing your work. Right. The thing about these symmetry arguments for the domain is they're usually pretty evident at a glance. So my rule on that is different. You don't have to explain why your region is symmetric. You do need to state that your region is symmetric, and you need to actually be correct about that. Right? But you don't have to give any justification. So all of this here is highly, I'll say, optional. It's here to persuade in the context of this lecture, but it's entirely unnecessary on an exam. Is that cool? Okay. All right. Okay, so we've got ourselves a symmetric domain. Let's see here. I claim that our function f. Keep in mind what our function is, our integrand. This f here. I claim that that's odd. Specifically, it has odd symmetry over the y-axis. Specifically, then, when I take this reflection. When I plug this reflection into the function, right, and you can see that happening here. I'm plugging in the reflection into the function. Then the value of f gets a minus sign. Right, and that minus sign is the oddness. Now there's some algebra in there that you kind of have to slog through. And by the way, this part is essential. You do have to give me the argument that the function is odd, because that's usually not evident at a glance. That's something that's it's true for algebraic reasons, and we need to see the algebraic argument. So you do have to actually crank that out. But notice how it plays out in this example that we take. Let's see here. Yeah. So I'm going to take minus x. That minus x goes in to where all the x's had been. Right? And so my function, getting my colors mixed up here. My function turns into this because I get a minus x there, and there, and there. Everybody see what I did? Plugging in the reflection. The reflection says everywhere you see an x, you put a minus x. Everywhere you see a y, you put a y. And so you get that, and then a little bit of algebra. The minus x quantity cubed is the minus of x cubed. Minus x quantity squared is just x squared. So that minus sign just kind of disappears. Sine of minus x is the minus. So a minus sign kicks out and cancels this minus. That gives you this plus here. And altogether, when it's all said and done, dust is settled, notice that this is the exact negative of f, and so minus sign. Everybody follow the algebra? Okay, so integral is equal to 0 by symmetry. Done. Game over. I didn't have to anti-differentiate anything. Right? I didn't have to plug in any bounds. Right? Take an even worse antiderivative after the first integral. No, just boom. Integral 0 by symmetry. You like it? That's pretty good? I'm a fan. a big fan. I don't know why books don't spend more time talking about this. It's a very powerful result. In particular, here's just my anecdotal experience of how powerful this is. So I've sat down and contemplated my own undergraduate experience, and where I had the second major in physics, which was a ton of math. No surprise, right? Tons of integrals, just endless integrals in the various physics classes that you take. And again, a lot of y'all are engineers and will be doing something similar. So my best estimate is that about 20% of the integrals that I experienced in my undergraduate physics major. That's a lot of integrals now. About 20% zero by symmetry. That's a ton of integrals. This one theorem saved me so much work. It's hard to. For example, if you think about it, I took 9 physics classes as part of my physics major. That means 1.8 physics classes worth of integrals were instantly done by this one result. Right? So, extremely useful. Okay. Now, that said, I do, again, need to see arguments. And so I'm going to make it very explicit here as to what I require for a symmetry argument to be a complete argument and therefore for full credit. You have to tell me what line of symmetry are you reflecting things over. What is the line of symmetry over which you're claiming a symmetry argument? I need to explicitly see what. So in this case, I would say, and I did here, the y-axis, right? That clearly defines what my line of symmetry is. Okay. You've got to give me the formula for the reflection. That's unavoidably important in the argument itself and proving the oddness. You need to state and be correct that the function is odd. Again, you can't just assert something that's not true for, right, obviously. But you got to actually put that down on the page that, hey, I claim this function is odd. But even more than that, you have to actually give me that demonstration. So that's this right here. Right? You've got to show that the function is odd, that is not obvious, needs to be demonstrated algebraically. And then finally, you also you need the domain to be symmetric, and so in particular you need to state that the domain is symmetric. So make sure to actually write that down. And again, you don't need to justify, right? Symmetry of the domain is usually, look at the picture, come on, it's perfectly clear. But you do have to state it, and you do have to be correct. Okay, all right. So those are the 5 components. For whatever it's worth, when I grade a question that has where the integral is computed by symmetry, and let's suppose that it's a 10-point question, let's just say, or that 10 points of whatever it is the question is, 10 points has gone toward the evaluation of that integral. Let's just say each of these would be pretty much evenly weighted. Each of these would be 2 out of 10. Right? So you really, none of these is a kind of a toss away that you can afford to just not write down. Okay. All right. For whatever it's worth, and again, this just kind of, I don't know. I think this is kind of funny. It happened to me more than once as an undergrad because I was a big fan of symmetry theorems, right? Big fan, and taking a physics test, they were notoriously long and tedious and involved, and speed was a big factor, and it was not rare for me to just not finish the test, right? And so it happened a couple of times that actually, I'm going to say several times that I had I got 20 seconds left and. I have to wrap this up, and there'd be an integral or two that I hadn't had time to evaluate, and so I just wrote equals 0 by symmetry and turned it in. And a couple times I scored. Right? So at the time, those instructors, now this was not a multivariable calculus class, this is a physics class where multivariable calculus is an assumption. Right? It's a given that you're right. So if it actually was 0 due to a legitimate symmetry argument, And if they were presuming my proficiency with multivariable, and I said it was equal to 0 by symmetry, in that context, that was considered okay. And so I actually got full credit for a guess, right? So anyway, and I'm all for that. Go ahead in your physics classes or engineering classes. Go ahead. If you got 10 seconds left and no idea on an integral, I think you could have a hard time doing better than just guessing equals 0 by symmetry and keep your fingers crossed. Hope it might work, right? But this is a multivariable calculus class, right? No such holes or would be appropriate here. And so that's why I emphasize you got to give me the argument. Because I didn't deserve those points that I got, right? And so y'all have to actually earn them. Okay. Now the other thing I want to point out about symmetry arguments, you do have to be really careful. They're dangerous in a way, and that is if you claim symmetry, but you're mistaken. Let's just say. Let's suppose that you just say, oh, well, yeah, and you go through and you have your 5 steps, but it turns out that the domain isn't symmetric. And there, therefore, is actually no symmetry argument. If you think about it, what you've written down about a symmetry argument, when there is, in fact, no valid symmetry argument, that's not progress toward a solution. That's progress toward a non-existent argument that does nothing. Which is what makes this such a dangerous thing, is that when a student incorrectly cites symmetry, nothing on the page is relevant to the actual solution of the problem, and so it's really brutal and it's really upsetting, and it makes me sad every time this happens. But there's nothing worth points on the page, right? So be careful, right? Double check your work. And after all, it is very quick. It's a very easy. You've saved yourself tons of labor. Invest a little bit of that saved labor in double checking and making sure that you're thinking correctly about the right line and that you have your formula for your reflection correct, and just think it through. Be careful, because otherwise, again, you can get yourself in trouble. Okay, now here's an example. Compute this integral here, and this is a hypothetical student response, and I just want to show you, how it'll be graded. So the student says that this domain here is symmetric. Okay, that's a pretty terse statement. Symmetric over what line? Right? It's not clear which. In fact, this domain has several symmetries. Which one are you talking about? Right? So there's a lot of ambiguity there. Next claim that the integrand has odd symmetry. Over what line? Right? So this is kind of hitting around what in fact are some of the right ideas. Indeed, this is a symmetric domain. Indeed, this is an odd function. But again, if you're not talking about which line, it could be that the line of symmetry over which this is odd is not one of the lines over which this is symmetric. Right? Who knows? We don't know if you know because this student didn't write it down. Right? So the student claims the integral is equal to 0 by symmetry. This integral is equal to 0. And there is a symmetry argument. Right? So but the student has only given me 2 of the 5. The student has told me that the domain is symmetric. Right? And the student has told me that the function has odd symmetry. But missing is what is the line of symmetry, what is the reflection, and the actual demonstration that the function actually is odd. And again, that's significant algebra and has to be shown. So this student gets 2 out of 5 of those 5 required parts. So you gotta give me a complete argument. Does that make sense to everybody? All right. Okay, here's another one. This one I'm going to do full up. I've got a domain bounded by certain curves. Here's the picture. I want to compute this integral here. Yikes. Right? No matter how you slice it, this is going to have corner issues. You could try to do a change of variables to turn this into a rectangle or something. It's harder than it looks. And this is a problem. So what I observe, and again, just casually looking at the picture, I see that line right there, and I just at a glance, I think, you know what? This looks like a Rorschach test, right? This is symmetric over that line, right? And I'm going to try to make a symmetry argument instead of tediously going through the brutal ugliness of actually cranking this out the old-fashioned way. So, going to need the formula for the reflection. How do we reflect over that line? Here's a picture that I find helpful. If you take a point x comma y, right? You think of the x and the y as making a sort of a little rectangular frame like that, right? It's I think a relatively easy pitch to reflect that rectangular frame over the red line here, because 45-degree line and all that. And from that, you can kind of just look at the picture and see that the x-coordinate of this reflection point, well, it's clearly negative, and it's a negative of the y-coordinate of the original point. So minus y. And likewise, the y-coordinate, clearly negative, and negative of the x-coordinate of the original point. So my reflection, negative y comma negative x. Okay. All right. Is everybody on board so far? Okay. Again, there's a bunch of discussion here as to justifying my claim that this is a symmetric domain. Again, not necessary. That's just there if you don't believe me. Right? That's there for teaching purposes, not for example purposes. You don't have to justify why the domain is symmetric. But you do have to state that the domain is symmetric, as I did here. And again, you have to be right. Okay. Then we need to know that the function is odd, and conveniently we have a formula for our function. And you got to be careful with this. Let me zoom out so I can fit all this in. Here's our reflection, right, that I need to plug into my function f, which is this thing up here. And let's slowly and carefully talk this through. In the first position, aka anywhere up here that I see x, I need to put negative y. And in the second position, aka anywhere I see y up here, I've got to put negative x. Does everybody see what happened there? Don't try to do this in your head. You're going to get confused. And furthermore, anything you do in your head and it's not on the page, I can't see it. I can't give you credit for it. So, but easy to mess this up, so think it through carefully as to what goes where, and this is what my function turns into. And then a little bit of algebra confirms that indeed this does have the desired odd symmetry. Roughly speaking, this minus sign here, let's see, that's the negative of x plus y, so negative 1 to the 7th gives me a minus sign there, right? And then let's see here. In fact, this right here, this was x minus y, and with all of these minus signs, it just straight turns back into x minus y. Nothing happened in that term, right? And I'll tell you what a lot of students will do wrong, and again, if you're moving too fast and not thinking through the details, a lot of students will look at 7 plus 3 and think that's 10, and so this is even. And that's just not how the algebra plays out. We've got a weird reflection. The algebra of the oddness is weirder than that. So there you go. And so integral equals 0 by symmetry. And I didn't have to integrate any of the ugliness or deal with any of the corners. Everybody okay? Yes.
I'm still a little bit confused about how the R of X and Y is negative Y, negative X.
Oh, yeah, so that's this picture up here. So here's my input point, X comma Y. Here's my reflection, right? And the claim that I'm making is that if I look at this kind of rectangular frame, and that there's X and there's Y, right? Actually, I'll tell you what, I can zoom in because we're just looking at just this one little part here. There we go. Yeah, so we've got X and Y. I assert that when you reflect this little L-shaped frame, it looks like that. You willing to believe that?
Yeah. Okay.
Yeah, and then it's just a matter of kind of looking, and you can use that as a guide and think through, which is equal to what and what's negative, etc. And yeah. Okay. Yep. All right. Okay, here's another example. And this is a dangerous one. This is what I like to call a landmine example. This is one that really looks like it's going to be symmetry. You can almost see the symmetry of the domain in these numbers here. Right? You see the 1 and the -1, right? You think, symmetric domain. Right? And then you look at your integrand and it leaps off the page. That's clearly an odd power. That's got odd symmetry. In some sense, I guess, right? But, so you see a symmetric domain, an odd function, and it's tempting to say integrals equal to 0 by symmetry. The problem is when you get into actually cranking out those details, it doesn't work. Because my domain, let's plot our domain. Our domain has, let's see, the corners are 0, 2, -1, 0, and 1, 0. Our domain has symmetry only over the y-axis. That's it. That's your only domain symmetry, the y-axis. Right? But on the other hand, this function here, y cubed, that's only odd if your reflection, you would need for your reflection to be x comma negative y. And if you think that through, x comma negative y, let's draw a picture of that. I can just come up to the same picture. X comma y reflects to x comma negative y. Looks like that. That is a symmetry through the x-axis, or a reflection over the x-axis. Not the same line. Right? So extremely tempting. And do not step on this landmine. Please, you got to be this is part of the reason I want students to show their argument. I think it through. The detail devils are real. If you think through the details, then you'll catch that, no, actually, there is no symmetry argument because these are different lines. So, losing. And so this integral you have to compute the old-fashioned way, and conveniently it's not that bad. But you can't use symmetry. Yep.
Why can't we just reflect over the y-axis? I know you would get the same, but...
Yeah, well, that's the problem. The problem is that if you use the y-axis, which the domain requires, right, then the formula for the reflection is that the reflection of x comma y is negative x comma positive y. And when you plug that into this, you get the y cubed turns into positive y cubed. It does not have odd symmetry. Yeah. So it just, doesn't work. All right. Okay. Lastly, I just want to point out, and this is very quick, there is an equivalent idea in 3 dimensions. It's exactly what you think. We reflect through planes instead of lines. Odd symmetry still means the reflection gives you a minus sign in the function. Symmetric domain still means that points and their reflections are either both in or both not in the set. The symmetry theorem is exactly the same. If you have an odd function and a symmetric domain, both through the same plane, the integral is equal to 0 by symmetry. It's exactly what you would expect. I deliberately wrote this down in exactly the same way as the two-dimensional theorem. And I deliberately wrote the warning down here exactly the same. It's got to be both conditions. It's got to be using both the same plane. Same 5 requirements, by the way, on an argument. What do you have to give me to have that be a complete argument? And as an example, think about this integral right here. And it doesn't look that bad until you notice that, wait a minute, my domain is a ball, which means there's square roots everywhere if I do it in rectangular coordinates. There's trig everywhere if I do it in spherical coordinates. I guess I could slog through, but wouldn't it be nice if there were an easy way out? And so what I'm going to do here is use the XY plane. I'll come back in a second and explain where I got that from. But I'm going to use the XY plane as my plane of symmetry. There's my reflection. The domain, being it is a ball centered at the origin, the domain's clearly symmetric through the XY plane. No problem there. No explanation required. Again, it's ball. It's got all the symmetries. Right? The function here is odd, because I can explicitly plug in the reflection into that function, right? That reflection, the minus sign here in that reflection, you can just track it through. It's right there. And I clearly get minus cubed, which is a minus, which is the minus needed for oddness. And so, sure enough, this function is indeed odd. Integral 0 by symmetry, no fuss, no muss, no trig, no square roots. No ugly, integration by parts or anything. Just boom. Everybody happy? Okay. Now, last thing I'm going to say real quick. Okay. I'm sorry. I did go over here. If you're curious where I got this choice, why did I use the XY plane? I kind of reverse engineered it. I was thinking as I go through this algebra, I was thinking, what do I want to happen in here? And it's you see this 3 here, and given that 3, I think, you know what, I'd really like to have a minus sign there. And knowing that you want to have a minus sign there means that motivates this formula for your reflection. And once you know the formula for your reflection, you can kind of draw the picture and persuade yourself of what your plane is. So my thought process was kind of like this. That's where I got the XY plane from. I saw the 3. I like the odd number. I want to get a minus sign attached to that exponent of 3, which happens by this reflection, which happens by this plane. Okay. All right. See y'all later. By the way, we're done with 5.5. So finally, y'all have a good one. See you later.